And so before we solve the thin lens problems, here's the these are the formulas and the sign convention that you should know. So first of all, let's take a converging lens, convex or converging lens. Remember, in order to find the position of the image and to understand the image formation process, you basically need two rays actually, P ray and M ray. So go back to the lecture and try to understand again. You may not need actually the F ray. And the relationship between object distance, image distance, and focal length is given by this thin lens equation, this formula, right? And the magnification, that means how big or how small the image is going to be compared to the object, is given by this formula. M is the magnification, is negative image distance divided by object distance, is also equal to height of the image divided by height of the object. Okay, so we'll be using all this formula, and this is the sign convention, rules to use the lens formulas, and all these rules are both works for both types of lenses, converging and diverging lenses. So first of all, focal length rules for focal length. Okay, if you're using converging lens or convex lens, the focal length is positive. Okay, if you're using a diverging lens, the focal length is negative. Okay, so magnification. If the magnification came out positive after calculation, that means you can definitely say the images are upright. If the magnification is negative, then you can say the image is inverted, right, compared to the object. Image distance. So if the image distance is positive, then the image is real. A real image will be formed. Okay. If the image distance is negative, however, the image is virtual. Okay. Object distance. So in most of the cases, actually, in all our cases, actually, the object distance is always positive because we're gonna use a real object, right? In very few cases, the object distance could be negative. Object distance, because in some very few cases object works as a virtual object, especially in two lens system, but that we're not gonna mention. Okay, here's the first simple problem. It says you have a converging lens given. A 3 centimeter tall object is placed 7 centimeter in front of a single converging lens, and whose focal length is 4 centimeter. Okay, I'm sorry, its focal length is 4 centimeter. Yeah. So object is, so this is the object, right? This is the object. This is the object, right? It's placed 7 centimeter in front of a single converging lens, convex lens, and it's asking these questions. So first question is, what is the location of the final resulting image? So that means the very first question is just asking di, the image distance. Di represents image distance. Okay, and this is easy. Just use the formula, lens formula, right? Lens formula says d1 over f is 1 over di plus 1 over do, right? And we're finding di, so 1 over f minus 1 over d naught, right? And di is 1 over f minus 1 over do inverse. And let's put the value. So focal length is 7 centimeter. That's what it said. But is it positive or negative? Since this is a convex lens, converging, right? Converging lens, because of our sign convention rule, focal length for a converging lens is positive. And object distance is 4 centimeter. Of course, it's positive because it's a real object. And the height of the object is 3 centimeter. So these are the given parameters. Let's put this back here. So focal length is 7 minus 1 divided by object distance is 4 centimeter inverse. So if you do that, so you're gonna get 9.3 centimeter positive. So the image will be formed 9.3 centimeter on this side, from the center of the lens, this side, somewhere here. um, okay, so that's the first part. So second part is, what is the total magnification, right? So total magnification will be, and just use formula. So since we have di and do, so just use one of the formula, negative di over do. Negative di is 9.3 divided by do is 4, right? So the magnification is magnification in this problem is negative 1.33. That's the magnification. Okay. So this negative sign simply means inverted. The image is inverted. Remember the sign convention, right? Image will be okay. Now part C is what's the height of the image. So then use one of the other formula. So height of the magnification is also equal to height of the image divided by height of the object. There's no negative sign for this second formula. So then height of the image will be, you know, m h naught. M is negative 1.33 times height of the object is 3. So it's gonna be about 4 centimeter. Okay, the height of the image will be about 4 centimeter. It's slightly magnified, you know, right? And again, negative sign simply means the image is inverted, right? Just like that. So E, we have already D actually. D, is the image real or object? Since the you know the most important fact to number to check is whether the image distance is positive or negative. Since di is positive 9.3 centimeters, since it's positive, that means image is real. Positive, right? Positive image distance means real image is found. E, is the image upright or inverted, right? And we have already answered that question. Since magnification is negative, image is inverted. Okay. And then finally sketch the final image ray diagram. So let me show you. So the final part. F part is, so again let me redraw the lens. There is the lens and object is placed here, right? And is focal length. First you have to define, once you draw the lens, first you have to define the focal point, focal length. It says the focal length is 4 centimeters, so this is the focus, and it's symmetrically both sides, right? And object is placed 7 centimeter. This is just, it's not up to scale, it's just approximate. 7 centimeter is your object distance. Now remember, you just need P and M ray. P means you draw a ray which is parallel to the axis, this axis, and we know that that has to go through the focus. That's why we choose P. This is called P ray. You need one more ray, which is M ray. So M ray means a ray that goes through the midpoint of the center of the lens, which goes undeflected, undeviated. And these two rays will meet, right, at point, intersect at point, and that's the position of the image that you can see. Okay, this is the image position. Okay, image will be from here. But remember, it's not just M ray and P ray. This is just for the technique to find the image position, right? But in fact, actually, this point, right, will be imaged by infinitely large number of light rays, you know, intersecting at this point. And this point again do the same thing. This point will image here. This point. So check my lecture slide to understand the detail of image formation process. Okay, so that's all you need to know. You just need to do P and M ray. Now next, similar, but now let's change the object position. Same converging lens, you know, but converging lens, but different focal length. And object is placed 4 centimeter, you know, in front of a converging lens, but whose focal length is, you know, 5 centimeter. So its focal length is somewhere here, right? That's the focal length. And object is placed in between focal point and the lens. So then it's asking the following same question. So first question is, what's the image position, you know, image distance. So again, 1 over di is 1 over f minus 1 over d naught. So di is 1 over f minus 1 over d naught, right? And 1 over focal length is 5 now. positive 5, right? And object distance is 4 centimeter. So that's your DI. So DI is in this case DI is negative 20 centimeter. So look at that. So image distance came out negative, right? So then you can clearly say the image will be virtual now, and we will see from the ray diagram what does the virtual image means. Okay, so that's the first question. Second question is, what's the total magnification? So magnification is, again, this is the formula, negative di over d naught. Negative of negative 20 divided by is 4 right, is 5. So negative positive 5, right? Positive simply means is upright, it won't be inverted. So in fact all the real images will be inverted, right, with respect to object, and all the virtual images will be upright. Okay, is opposite with the magnification. So C is, what is the image height? So again use the second formula, S I over S naught, right? So HI is M H naught is 5, S naught is 2 centimeter tall, so 10 centimeter tall. Okay. Is the image real or virtual? So we have already answered that question. Since DI, which is the image distance, is negative, right? That means the image is virtual. Okay, the image will be virtual. E, is the image upright or inverted? We have already answered that question. So since magnification is positive, image is upright. Upright image will be fine. We will see in the final ray diagram actually. Okay, so now next is next question, final question is, sketch the ray diagram, final image. Okay, so let me do it again here. The last one is again draw the lens. Now the object position is, so you have a focal length something 5 centimeter, right, both symmetrically, but you're placing your object a little closer, right, in between focal point and the lens, like this, right, because this is your object distance 4 centimeter, whereas the focal length is 5 centimeter. So then do the same thing. You need a P ray, right, and that has to go so it's not, you use a ruler, you always use a ruler for a nice diagram. And the next ray, this is a P ray, the parallel ray. The next ray you need is the M ray, middle ray. So it has to go through the middle of the. Now you can clearly see, right, these two rays will never meet here in this side. So that means since these rays will diverging, right, diverge, they never meet here. That means the image will be definitely virtual. So if someone is looking from here, this is the observer, it just appears from this side, right? The image will be from this side. That's why it is called virtual. Because why? Because the image will be from the diverging ray, and the image formed by diverging rays are, virtual. And how do you find the position of the final image? Then since it's virtual, you just need to extrapolate these virtual rays. You just need to produce them backward like this with dotted lines. That means virtual, like this, right? And they will meet at certain point, but just use the dotted lines. So this will be the final image. You can clear, and it's nothing. It's just simply a magnifying glass. In this position, it just works as magnifying glass. Okay, and the magnification is positive, so 5 times actually, right? And that makes sense. So the image, this is virtual. We saw from the mathematics, right? This came out negative. It's virtual because virtual and upright. It simply works as magnifying glass. So here's the next problem, similar problem. It says a stamp collector uses a magnifying lens, magnifying glass that sits 2 centimeter above the stamp. So that means your object distance, which is of course positive because the object is real. The stamp is, this is the object. The object is sitting here. Stamp is 2 centimeter, right? That's our object distance. And the magnification he saw was +4, right? It's because since it is using as a magnifying glass, you want positive magnification. And based on this, what is the, you know, what is the focal length of the lens, this lens? Then to find the focal length, since you already know the object distance, you need image distance. So how do you find the image distance? Just use this formula, right? And then di is negative m d0, right? So negative magnification is 4 and do is 2, so negative 8 centimeter is the image distance. Then once you have that, then you can find the focal length from using the lens formula. So focal length is 1 over do plus 1 over di inverse. So put all the numbers. So 2 minus of minus, remember minus of minus gives positive, right? And don't forget the minus of minus, and that's gonna give you 2.67 centimeter positive. Okay, so the focal length for the given lens, this magnifying glass lens, is 2.67 centimeter, and this positive focal length proves that this is a converging lens, right? Because converging lens, magnifying glasses are always converging lens. So before we do some diverging lens problems, so these are some examples of how the image distance changes with the object distance, for different cases. So what I'm doing is, for the given lens, same lens, I just change the object distance at different. So if you put, so for example, if you put an object between f and twice f, right, then the image will be formed beyond twice the focal length, right? And this is the p ray. What you need is you just need p ray and m ray. Okay, that's it for all, right? And what happens if you put as twice the focal length? The image will be exactly formed at twice f, equal distance. So object distance and image distance will be equal. And next is we just saw actually for magnifying glass, right? If you put an object in between the focal point and the lens, then the image will be virtual and magnified on the same side. So that means it would just works as a magnifying glass. And you can you can try putting an object many different positions, and then try to figure out where the image will be formed. Now finally, let's do one problem on diverging lens or concave lens. So here's the problem. A 5 centimeter high object is placed 15 centimeter from a 30 centimeter focal length diverging lens, right? And determine the image distance, the magnification of the image height, and the properties of the image. So diverging lens means, let's first draw the ray diagram. I mean, here's the diverging lens shape, right? It's concave shape, and this is the axis, our principal axis. And it says, so based on this, so it has a 30 centimeter focal length. So focal length on both sides, right? This is the focal length, focal point. An object is placed 15 centimeter, right, from a 30 centimeter focal length. So 15 centimeter means the object is placed right here, right? So then how do you find the image position? So this is the object, real object, right? So again, you just need P and M rays. So for P ray means you, from the center of the lens, right? So you draw a P ray which is parallel to the principal axis, and that has to, now it will not converge, it will diverge, right? It will diverge, but how? It will diverge so that it appears to come from this focal point. So you have to, so it diverges so that it just appears to come from on the focal point behind the lens, same side of the lens. So draw, since this is a virtual focus, you have to do a dotted lines. That's the P ray, and you need M ray. M ray means now you draw a ray directly passing through the for the center of the lens, and it will go undeviated. This is M ray. That's it. That's all you need. So they intersect at this point, and then draw, and this is on the same side as object, so this will be virtual. and upright. You can clearly see they intersect at that point, and this is the image in this case. So this is how you draw the ray diagram for a diverging, right? Diverging, or it's also called concave because of its shape, right? Okay, let's answer that question first mathematically. The image distance. So you're given the focal length and 30 centimeters. So be careful because since it's diverging, you must put the negative sign, otherwise it won't work. The object distance DO is 15 centimeter, and of course it's positive because object is always real. And then find the image position. So just use the you know regular formula. The same formula will work. Right? Same formula. Di is 1 over f minus 1 over do inverse, and 1 over focal length is negative 30 centimeter minus 1 over 50 negative. So di, right, calculate that, is going to be negative 10 centimeter, and you can right away you can say the image will be virtual. Image is virtual and upright. So we will prove that in a second. So that's the first part. Second part is what's the magnification is again negative di over do. So negative of negative 10 divided by do is 15 centimeter. It's plus 0.67. That's the magnification. It's a diminished image, right? Because it's less than 1. So positive sign simply says the image will be upright, right, as we can see here. So your observer is right here. Right, you will see a diminished small size image of this object. Okay. So next is image height. So image height is, so use this formula hi over s naught, right? So hi is m s naught. M is magnification is 0.67. We have just calculated. S naught is 5. So it's 3.3 centimeter. Okay, it's diminished. You can clearly see. And the nature of the image is, so as we already told, actually is the image will be virtual, upright, and smaller in size. Okay, so that's all you need to know.